Welcome back. In the last lecture, we have seen how while imposing various kinds of constraints on the accessibility relation is leading us to different axiomatic systems, like T requires reflexive relation, S4 requires transitivity, whereas B requires symmetric property, etc. So in this class we will be talking about one of the important methods, decision procedure methods, that we are using it for this course. So that is semantic tableaux method. So a little bit of history about semantic tableaux method. It was introduced by many people around the same time. The credit should go to Raymond Smullyan, Hintikka in his model sets. They are proposing the same kind of idea, and it was later used by Melvin Fitting and all others in US in particular. So this and Beth is another important logician whom we need to credit for this semantic tableaux method. So the idea of semantic tableaux method is simple and straightforward. Just as in the case of propositional logic, if you want to show that a given formula is valid, or tautology, all tautologies are valid formulas, what you do is that you negate the formula and start constructing tree diagram. It's a upside down kind of tree, and then you see whether all the branches closes or not. If all the branches closes, that means not of x is considered to be unsatisfiable. If not of x is unsatisfiable, guarantees you that x is considered to be valid. Similar kind of thing we do here in this case as well. So what we are going to do is that, so we have different axiomatic systems K, T, D, S4, S5, etc. Now while constructing the tree diagram for these things, while negating these formulas, we will see what kind of constraint we need to impose so that the branch closes. So before that, I need to talk about some of the important tree rules, so that all the tree rules with respect to the propositional logics are intact, but we need some more rules with respect to necessity and possibility. So before I begin, the idea here is this thing. So K is the one which we began with. It has a characteristic axiom. It is necessary that P implies Q means it is necessary that P implies it is necessary that Q. It does not require any constraint on, we do not have to impose any constraint on the accessibility relation. So whereas in case of D, it has to be serial. I mean the constraint that you need to impose on the accessibility relation has to be serial. Serial in the sense that for any given world, there has to be at least some one world y, and where this x is accessible to y. There should always exist some kind of world y such that x is accessible to y. For any given world x, there is always some kind of world y in which x has access to y, or y is accessible from x. They are all same things. So then that is considered to be D. So interestingly, this axiomatic system was introduced before T. Sometimes reflexivity and seriality sometimes leads to some property called seriality. So anything which is valid in K has to be valid in D, and it has to be valid in T also. So anything which is valid in D has to be valid in T. Then it goes like this. S4, we have S4 here, and then we have something called S5, and then we have some other axiomatic systems like B, which requires a symmetric property, and then this leads to this one. So this together with 4, S4, 4 leads to S4, and then D together with T leads to B. B is nothing but T stood B. B has this axiom, corresponding axiom. It is something which is the case, implies that it is possible that phi has to be necessary. So now what we are going to do in this class is that you list out all these formulas, and we will see while negating these formulas what are the things, what kind of constraint you need to impose on the accessible relation is the one which we are trying to see here. So now before that we need to talk about some rules. So we are all the tree rules for propositional logic are same here. and they are going to be like this. So we have something called alpha rules and we have beta rules. So if a formula is there like this, alpha, then it is same as alpha only. Then alpha or beta, it is considered to be a branch, and alpha and beta, it is a trunk of the tree. It will be like this. The tree diagram for the basic formulas that exist in your model logical system, they are like this. Now alpha implies beta is not alpha and beta, and then alpha if and only if beta is like this. Both alpha and beta has to be true and not alpha, not beta. So there are said to be some kind of alpha rules because we are talking about positive things here. So exactly the negation of this one is like this. Negation of alpha, you substitute it as just alpha, and negation of alpha or beta, it is a conjunction. Negation of disjunction is conjunction, and you need to write like this. Negation of alpha followed by that negation of beta. What it means is that both have to be true, so that this is going to be true. And negation of alpha and beta is a branch which consists of these formulas. So negation of alpha implies beta is nothing but alpha and beta, and then negation of alpha implies beta is alpha not beta, or you can take even not alpha beta also, not alpha beta. So these are the things that we have in the case of classical logic. So now we have these two things, necessity and possibility. So now we are talking about S5 system, particularly when we are talking about, let us say you are talking about S5, and these are considered to be the rules. All the rules of propositional logics are intact. Together with that, we have these rules. There is something called as modal negation. Suppose if you have a formula like this, the modal negation of this one is like this: negation of necessity of alpha. So if any formula, such kind of formula exists, then you need to simply replace this thing. Negation goes inside a little bit, negation goes inside, and negation of necessity is going to be possibility, and you have to push this negation inside. So this is going to be like this. And necessity of it is not possible that alpha. So this is this can be written as necessity not alpha. So this is with respect to modal negation. And there are some rules which are considered to be this thing, possibility S5. So this is going to be like this: if any formula alpha, possibility of alpha exists, then you replace it with alpha, but you need to ensure that this suppose if this is the world W, this says that possibility of alpha is true in a world W, you replace it, then it will become alpha is true in a world V, but this V is new to the new index. V is considered to be new to this path of the tree. So the idea here is that suppose if you have two formulas like this, possibility of alpha and possibility of beta, for example. First time when you remove this thing, you choose one letter U, and you are not supposed to use the same kind of U again. When you remove beta now, it has to be beta, and there any other letter other than U is the one which you need to take into consideration. B has to be true in any other word. So no two possible words will be alike. So if possibility of alpha is there, you can replace it with alpha, but V has to be new. This W is accessible to V. Whereas necessity of S5, I have to draw a line like this so that it will be clear. Necessity of S5 rule. So this tells us that if a formula necessity of alpha has to be true in a world W, by the definition you can say that necessity of alpha is going to be true in a world W only when alpha is true in all possible worlds. So that means this alpha has to be true in a world V. So this V is any indexical letter that exists in the in that given path of your tree. So V can be any index. So that means for all such kind of V's, it can be V1, V2, V3, anything, all those things your alpha has to be true. And these are the things which are related to necessity S5 rule. So there is one more formula which we use, that is what is called as closure of formula. If you come across a formula alpha and you also come across a formula not alpha, which is also true in a world W, then this is called as closure, because this is leading to inconsistent kind of situation. Now the only formula which is new here is this thing. This is what is called as necessity T rule. So this is an interesting rule which suggests us this thing. Necessity of alpha is true in a world W. When we say that necessity of alpha is true in a world W, if alpha is true in all the worlds that W has access to. If W has access to U, it has to be true there. W has access to V, in V also this alpha has to be true. So now if you come across a formula necessity of alpha is true in a world W, then T rule tells us that this alpha has to be true in that world itself. So it is like necessity of alpha means it is true in this one, etc. Let us say this is U2, U1, etc. So in addition to that thing, if you have a necessity of alpha which is true in a world means, and this alpha is true in this world itself, then you are following some kind of reflexivity relation that is nicely mentioned by this rule. Whenever you come across a formula necessity of alpha true in a world W, you replace it with alpha and put the same index. So that will serve our purpose. So now using these rules, let us talk about the formulas that we have seen. Why it is the case that simple formulas like necessity, we will begin with the simplistic kind of formulas like this thing. So this is an axiom in T. So now we are trying to show that this is going to be invalid in K, and we will construct a counter example, and then we will nicely draw the relational structure which is due to Kripke. So now in the semantic tableaux method, the first step is to negate the formula and start constructing the tree based on these rules. So this is like x implies y. So this is and not phi. Sorry. So this symbol is this one. Necessity of phi implies phi. So now the simplification of this one is this, because the negation of x implies y is nothing but x and not y. So you have used the same thing here and we have written like that. And you need to note that in modal logic, unless and until you mention the world that you are in, it doesn't make any sense. So modal logic, you only talk about truth with respect to the worlds. These are considered to be possible worlds. Till now we did not define what exactly we mean by possible worlds. We will have another special kind of lecture on the possible worlds, and then we will be introducing the concept of there is a view which is dominant in philosophy in particular, that is what is called as modal realism. Would you do you treat these possible worlds as real as the concrete things, you consider it as concrete, or you have to treat it as an abstract kind of things. So these are some of the questions that we will answer it, and then we will deal with such kind of questions in a separate lecture, and that lecture is based on possible worlds and modal realism. So now coming back to this one, this is true in a world W. So this is the case. Now necessity of phi is true in a world W. So now we need to put like this. Okay. So now there is no way in which you can close the branch. There are two things which you require. So whenever you have necessity of phi, this doesn't imply that there is always some kind of world which exists out there, and in that world phi is true. That cannot be the case. Whereas if you say possibility of phi, it should be the case. There is no other way in which you cannot say that there is no world such kind of thing. So there is always some kind of world, and in that world phi has to be true. but in this case you cannot say anything. But when you say possibility of phi is true in a world 0, means there should always be some kind of world 1, where in that world 1 the phi has to be true. That is the only difference between these two things. Is like the difference between universal quantifier and the existential quantifier. You can talk about, you can assume the things to be like this, all unicorns are intelligent to be the case, but the moment when you talk about there exists some unicorn and that x is considered to be intelligent. For example, if you write it like this, unicorns are represented like this. If x is a unicorn, x is intelligent because you and I are considered to be predicates. On the one hand, we have another statement which is like this, x is unicorn and x is intelligent. The moment you say this, there exists some x, that means it presupposes that your unicorns has to exist in the world. So this is a big kind of fallacy which is called existential import, existential fallacy, which we are not going into the details of it, but the idea is same here also. Whenever there is a possibility of any formula, it is already presumed that you can assume that there is already a world which is accessible to that one. So that's the reason why we say it is possible that it is raining outside. It means that there is already a world in which it is raining is considered to be true. In the actual world, it is not the case. So if it so happen that this formula remains open because there is no, we are not able to say that you cannot reduce this thing necessity of phi to phi. So now the counter example in K system could be like this. From the open branch you can construct a counter example. Now the counter example is going to be like this, not phi. Of course it is not accessible to anything, you can just leave it like this and you can say this thing W. Simple example is this thing. So now why this will serve as a counter example? So now we substitute this thing again into this one. There is only one world and in that world not phi is true. Now coming back to this formula, necessity of phi implies phi. So as I said in the last class that if there is no world which is accessible to this one, then all the formulas that begins with necessity are going to be true and all the formulas that begins with possibility are going to be false. So in that case it is considered to be T. Now and phi, where phi is considered to be false here, phi is already false here. So this is true and this is false, this makes the whole conditional false. So the counter example, the relational structure that you can draw is only this one. So now what happens, under what conditions this branch closes? This branch closes only when if there is a world W and that W is accessible to itself, and if it is accessible to itself then necessity of phi, that means phi has to be true in that world W itself. So the moment you draw something like this, W is accessible to itself, then your phi has to be true in that world W. So now you have not phi is true in a world W and phi is true in a world W and this closes. So under what conditions we close this thing? When accessibility relation is reflexive, then only the branch closes. Not x is going to be unsatisfiable only when you impose reflexive, you impose a constraint in the form of reflexivity on the accessibility relation. So that means this formula holds only in reflexive frames. So now let us consider another example where we will see why it is a case that this formula, which is characteristic of 4 axiom, so that is necessity of phi implies necessity of phi. That it is necessarily true has to be necessarily true. So what it means. So now again you begin with the negation of this formula, then it leads to this one. So second step, 1, 2. So in semantic dialogues method you start with the denial of the formula and then ultimately what you show is that not x is unsatisfiable. That means all the branches closes, it becomes unsatisfiable. If not x is unsatisfiable, what is satisfiable is not of not x. Only if you remove all the possibilities of not x, you will come to x. So that's the idea here. So now you expand it a little bit further, then it will become this not of two necessities and then phi. So now we have to simplify this thing. All these things are true in a world, assuming that these are true in a world W. Now first time when you use a negation thing, you have to push this negation inside, and negation of necessity will become possibility, and then you are pushing this negation in between this thing, then it will become like this. First time when you apply this one. Now second time when you do it, negation of necessity of phi. So you have to have another possibility, because negation of necessity is possibility, and you are pushing this negation further inside, then it will become like this. Two possibilities and then not phi. So now there is a formula with which you have this thing, necessity of phi, and then you have this thing. So now let us remove this possibility operator by using the rules that we have here. So possibility of alpha, when you come across a formula like this, it is true in a world W, then you can simply replace it with alpha, but that V, the world V where the alpha is true, has to be new. So now first time when you remove this formula, then it will become, you have to write like this. So I will mention it here because of the space problem, I will consider this here. So this will become like this. So I am just writing it here. So we have possibility of not phi, and then we have necessity of phi, which is true in a world W. Now first time when you remove this formula, then you have W is accessible to V. So you take a letter V, and then in that world V, this possibility of not phi is true. So now next time when you remove the same possibility operator, diamond operator, then you are moving from V to another world. So that means V, this V has to be accessible to something, some world randomly I have taken into consideration T, and in that world T, not phi has to be true in a world T. So now what we have is this thing, if some formula possibility of phi is true in a world W. So now we apply then the T rule. The T rule says that whenever you have a formula necessity of phi is true in a world W, it is already taken into consideration that it is already a reflexive kind of relation, and then where you don't achieve anything even if you take this thing into consideration. Suppose if necessity of phi is true in a world W, and then what you get is phi is true in a world W, there is no way in which you can close the branch. So the idea here is that negation of the formula, and then we are questioning under what conditions this branch closes. So now W is already accessible to V, that means necessity of phi, this phi is true in a world V, and necessity of phi is true in a world W means wherever this W is accessible to, in that world it has to be true. Now this branch will remain, it closes only when the accessibility relation is considered to be transitive. So this goes like this. We have taken three worlds W, V and T. Let us say T is the world which we have taken into consideration. This is W and V and T. So W has to be accessible to V. So this is the one which we have, W is accessible to V, and you see here V is accessible to T. But in this case there is no way in which you can move from W to T unless and until you bring in the transitivity relation. The transitivity relation is this one, which I am drawing it like this. Unless and until this happens, if W is accessible to V and V is accessible to T and W has to be accessible to T, then that is considered to be transitivity property. If there is no transitive property, this branch will remain open. So now the idea here is that we have WRV and VRT, and that should imply WRT. So this is what is transitivity property. Only when you invoke this thing, the branch closes. If that is the case, then your phi has to be true in that world T also. Only in that case your phi is going to be true there. In that case it closes. So what did we get out of this one? So if you deny the formula with this thing, that it is necessary that phi means implies that whatever is necessary has to be necessary. It closes only when you impose transitivity relation on the accessibility relation R. If the accessibility relation is transitive in this sense, then only it closes, otherwise it is going to remain open. Suppose if it remains open here itself, then it is going to be invalid in T. So why? Because there is no way in which you can close these branches, and from the open branch you can study the counter example, and this counter example can be represented in terms of Kripke structures like this. A Kripke structure should have possible worlds first of all, and then you need to know how these worlds are related to each other. That is what we have, and then we need to know where your atomic formulas are true, in which world a given atomic sentences that exist in a model logical formula are considered to be true. So let us consider one final example, and then we will see why it is the case that this particular axiom requires symmetric property or any other property. So that we are going to see. So now suppose if you have a formula like this, if phi is actual truth, with this we will end this lecture. So if phi is true implies that it is necessary that possible that phi. So now under what conditions, in which axiomatic system it is going to be true, that is what we are trying to see. Is it true in T, K, B, C, B, D, etc. So now again you deny the formula and start constructing a tree, then it will become like this. So all these things, let us assume that they are true in a world 0. You can take W, you can take alpha, gamma, it does not matter. So now negation of necessity, possibility of it, this goes inside, and then negation of necessity will become possibility, and this one possibility negation, possibility phi. So now if you simplify it further, this will become negation of possibility will become necessity, and then this one. So now you have to reduce this thing, you have to remove this possibility, necessity operators, etc. So now till now we are in a world 0. So now we have a possibility operator, that means you can go to another world 0 or 1, and in that world 1 your necessity of not phi has to be true. So this can be depicted like this. So the moment you have possibility of some formula x, you have to go to another world W where this x is considered to be true. So these are different worlds W and W2. Necessity of negation of alpha. Now there is a rule, T rule, which tells us that whenever you have a formula necessity of not phi is the case, you can simply substitute not phi. Actually this is true in a world 1, and this has to be true in a world 1. Already it is reflexive relation. So then only this holds here. Now, but that is not going to serve our purpose, because you have phi is true in a world 0, phi is true in a world 0, and not phi is true in a world 1. So when this branch closes is the one which you are trying to study. So this branch closes only when we have a relation like 0 or 1, and if it so happens in that one, the world 1, necessity of not phi is 0. If 1 is also accessible to 0, it so happen that, let us assume that this is 0 and this is 1, and if 1 is also accessible to 0, in that case necessity of phi is true in a world 1, it has to be true in a world 0 also, because 1 is also accessible to 0. So this is what is symmetric property. Only when you invoke this symmetric property, then there is a way in which you can move from world 1 to back to 0. So in that case your phi has to be true in a world 0, not phi has to be true in a world 0. In that sense this branch closes. So with this we will stop. In this lecture we have just considered the semantic tableaux method, with which you are just trying to see various axiomatic systems that we already studied in somewhat detail when we are talking about when we considered axiomatic system for these modal logics. So what happened now is that things have become simplified in a sense that depending upon you, if you just know if you have some set of words and how these words are related to each other, and if you have an accessibility relation, etc., then you can say when a given formula holds in which kind of frame. T holds in reflexive frames, whereas B holds in symmetric frames, etc. So I stop here. Thank you.